Last time we met, we covered topics in chemical foundations, which included the elements, their names and symbols, how they got that way, how we know that they're that way. And today we're going to look at how we name compounds. Learning the chemical symbols is like learning the alphabet. Nomenclature is more closely related to how to write words. So when I say hill, you automatically know H-I-L-L. Hopefully, by the end of this chapter, when I say sodium chloride, you'll automatically do this. That's it. All right, and there's a buffer day built in. This is Tuesday. Thursday, there's a buffer day, and we may get through nomenclature today. I'm not going to hurry because I want to hit these points and drive them home, so to speak. So we may split the chapter and we may not, but if we don't, then I'll come back on Thursday and start the review, and that will give us 2 days for review. Reviews sometimes take a little longer than lectures. Lectures is just introduce the material. Reviews, doing your homework, working problems in the review document, and the review, that's where you learn chemistry. This is just an introduction to give you the rules and the concepts. So nomenclature, chapters 4 and 5 are going to be in exam 2. So it's all naming compounds. So before we get into the meat of this slide, compound names, some of them were inherited from medieval times. And what we tried to do in modern chemistry is to standardize some of those names and make them extensible so you could name other compounds with a pattern, with a set of rules where you and other scientists could communicate the names of the compounds and what compounds you were discussing. Because if you know the name, it's like if you know a person's name and you've known them for a while, or you talk to people about them, you hear their name, you instantly have an idea of their personality, their accomplishments, their shortcomings. And we can look at compounds in a similar way. We want the name of a compound to be unambiguous. What that means is the name of a compound can only designate one formula for that compound. Can't be anything else. If the name suggests alternate compounds, then it's not to be used. Also, we don't want our compound names to be redundant. In other words, if the simpler the better. The simple name gives you all the information you need to identify the compound, then you don't want to add any information that's unnecessary. Okay, so those two rules are override any type of naming. And by the way, names for compounds were and are standardized by an organization called IUPAC. This is International Union of Pure and Applied chemists. And they have several subcommittees that are assigned tasks of standardizing names for one thing. They do a number of other things, but they have subcommittees that handle naming compounds. And they have, I'm sure they have subcommittees that are tasked with naming organic compounds because they can become extremely complex. We're not going to go there. We're going to keep it simple and start with binary compounds. What's a binary? A binary compound has two parts. And in the beginning, it's two elements. Those compounds can either be ionic, that is, they can be a metal and a non-metal, right? Or they can be covalent. What we mean by covalent is the ionic compounds are formed by transfer of electrons from one element to the other. So for instance, with sodium chloride, we would transfer from the metal one electron. Now that makes sodium positive because it has an excess of one proton, whereas chlorine now has an excess of electron. Okay, then the attraction between the two is electrostatic. Those are ionic compounds. Covalent compounds are formed from two nonmetals. Now, since nonmetals tend not to want to give up their electrons, they compromise, they share electrons, and that's how the bond is formed. So for instance, if you have carbon monoxide, you have carbon and oxygen, they share electrons in such a way, and each one of these lines is two electrons. To have a bond, you need two electrons in a covalent compound. So they have a triple bond between carbon and oxygen. They share electrons, but those are two nonmetals in binary compounds. Okay, when we look at the periodic table, we know where the metals and the nonmetals are located because we talked about that. We have that zigzag line down through the periodic table that differentiates between nonmetals on the right and metals on the left. Okay. Now, I'm going to need the whole board, so I got to erase this stuff. All right, for binary compounds, we're going to start off with, there are three types. Type 1. Metal and non-metal. Okay. The metal in a type 1 binary compound is capable of having only one charge. And these are ionic compounds, metal, non-metal. So the metal can only have one charge, and we know what that charge is based upon where it's located in the periodic table. So the group that has sodium in it, the alkali metals, always have a +1 charge. Okay, so alkali metals always +1 charge. Alkaline earths always 2+ charge. That's the second column over. Sodium's in the first column. The next column over is alkaline earths. Then we skip over to the boron group. They don't have a name, so we just say the boron group. Now, technically, boron is a non-metal, but it can enter into ionic compounds because it's right on that line. So we could consider it a metalloid. In other words, sometimes it acts like a metal, sometimes it acts like a non-metal. In our discussion here, it would be a metal. And they always have a 3+ charge. That includes boron, aluminum, gallium, and indium. Had the 3+ charge. Then we go over to the non-metal side. And it's not important. Well, it is important that we understand what's their potential charge. So the halogens, starting with fluorine, chlorine, bromine, iodine, they're 1- charge. Fluorine is definitely 1-, always. Chlorine can vary, but it only varies if it's in non-metal covalent bonds. So as long as it's in an ionic compound, it's a -1. Then we move over to the left to the chalcogens, the oxygen group. They're 2- charge. Then we move next to them are the pnictogens. Oops. Let's do better than that. Pnictogens, 3- charge. Now the carbon group is kind of straddling the line between the two as far as charges go. So we don't assign a charge to carbon in this case, or any of its members of its group. Okay, so the type 1 compounds have metal, non-metal, and the metal is fixed charge. It only has one possible charge. That identifies the type 1 compound. Type 2 compounds they're also metal and non-metal. The difference being that the metal could possibly have 2 or more charges depending on the compound. Now, once the metal is in the compound, its charge doesn't change. But as it transitions into the compound, it could have 2 or more different charges. That's what we mean by variable charge. Okay. So now when we metal, non-metal, when we name this compound, since the metal has a fixed charge, all we have to do is say, what is the metal? For instance, sodium. Do better than that. Sodium. And then the second part of the name, the anion, this is the cation. The anion, instead of saying chlorine, we change the ending to IDE, chloride. This is the anion. Okay, so sodium chloride, and since it only has that positive charge and chlorine has a -1 charge, we write the simplest ratio of cations to anion that balances charges. So 1 sodium plus, 1 chloride minus, that makes the simplest arrangement, and the charges are balanced. All compounds are neutral. Right? Physicists deal with electrostatic imbalance, right? But chemists deal with ultimately neutral situations. This is neutral. What if we had something like this? I'm gonna write it over here. Say I give you this one, calcium, that you would name it calcium chloride. We know that's all we need. That's an alkaline earth. Calcium is a 2+ charge. Chlorine is a -1 charge. We balance the 2+ with 2 minuses. So calcium chloride is both unambiguous and non-redundant. So what would I do if I wanted to make it redundant? I would use the rules from type 2. Type 2 compounds, we have to indicate the charge on the cation, on the metal. For instance, if we have this one, okay, we would name that iron oxide, and we would find out what's the charge on the iron. We have to deduce the charge. So we know that oxygen is 2-, right? That makes 6- over here, 6+ to balance it. That means each one of these has to be a 3+. 2 times 3+ is 6+. So we say Roman numeral 3, iron 3 oxide. That tells us the charge on the iron. That way we're both unambiguous and non-redundant. Now, if we did the same thing over here, if we said calcium 2, that would be redundant. We don't need to say that because calcium can only have one possible charge. So that would be, for instance, answer on a test would be wrong if you put a Roman numeral 2 in there. All right, that belongs over here. So what if I said, let's see. About, oh, here's one. How about this one? Name this one. Okay. Remember, with your periodic table, this is one group. I left those out. There's a special group here in the transition metals. Most of the transition metals have multiple possible charges. Transition metals. Transition elements. Fit in the type 2, except for 3 elements. One of them is silver. Silver always has a +1 charge. So we would just say silver chloride. That's it. The other 2 elements are cadmium and zinc. So over here we have silver, cadmium, and zinc. Let's see. Let me check myself. Be sure I'm not telling you wrong. Yeah. This is a fixed charge of +1. This is a 2+, and this is a 2+. They're fixed charges. Okay. The rest of the transition metals have variable charge, but those 3 have fixed charge, so they fit into the category type 1. Okay, so that's a type 1. I don't want to leave it over here. That's one example. We'll have some other examples in subsequent slides. Okay, so that's type 2. You'll never guess what type 3 is. Non-metal, non-metal. These are the covalent compounds. Let's see. All right. Those give you examples of how you would name the metals. Always, we just write out the element, and the anion, the non-metal, we had IDE on the end. So hydrogen is a funny one. Hydrogen is a fixed charge, but it's not technically a metal. But when it becomes associated with a metal in a compound like this one, aluminum with 3 hydrogens, now the aluminum assumes the positive charge and hydrogen has to be negative. 3 negatives balance the 3 plus. Okay. So in this case, we would name it aluminum hydride. Okay. All right. Let's see. That's just another example. Rules for naming type 1. I've given you these rules. Here they are on the slide so that you can go back and review them. Type 1 examples. Okay. Now, is this right? Potassium is the metal. Chloride is the nonmetal. That's true. But is potassium a type 1? Does it make it a type 1? Yeah. Potassium is an alkali metal. It's always +1 charge, so that's true. Magnesium is an alkaline earth. It's always 2 plus. Bromine is a -1 charge. So we've balanced the charge with 2 negatives against 1 metal that has a 2 plus charge. Magnesium bromide is correct. Calcium oxide. Calcium is 2 plus, oxygen is 2 minus. We only need 1 of each. Okay. How about this one? How about this SRBR2? Before we get to type 3. SRBR2. What you want to do when you're trying to name a compound is first, is it a metal, non-metal, or a non-metal, non-metal? Binary compound. If it's a metal, non-metal, then you have to decide, is it a 1 or a 2? Look at the metal. Is the metal fixed charge or variable charge? This one is SR. You look on your periodic table, and you've already memorized that one, so you should know where to find it. It's an alkaline earth. It has a 2 plus charge. And that should be obvious because this is a 1 minus charge. But it's also a fixed charge. So that makes it a type 1 compound. And we just call it, well, it should be coming up, strontium bromide is the proper name. Okay. Here's your type 2 compounds, where you have metals that could possibly have more than 1 charge, depending on the compound. We put a Roman numeral in the name to designate the charge on the metal. Right? There are the various charges. Now, the old convention had the lower charge was an OUS on the end, and the higher charge was an IC on the end. That's the way I learned it. But ferric means a +3 charge, but cupric means a +2 charge. So the IC is not fixed in its meaning, right? This is probably held over from medieval times. And it was decided that the Roman numeral convention would be less confusing, right? So, by the way, when you name those compounds in your extra credit exercise, 50 ways to name a compound. If you give me ferric chloride, or give me stannous bromide or something like that, I know that you looked it up. You didn't name it yourself. So I'll count that one off. If I can determine that you cheated on that one, then you won't get credit for it. Just a word of warning. Name them yourself. Learn the rules. That's the whole purpose of the exercise. Not just to give you extra points, it's to help you learn how to name compounds. All right. So here we have type 2 compounds, and we've discussed them in nauseating detail already. Examples. Now, is this true? Is copper variable charge? You can look on your periodic table, find the copper, and look in the upper right-hand corner and see, does it have more than one charge? And as a matter of fact, it does. It could be a 1 or it could be a 2+. So copper 1 bromide is correct because 1+ balances a 1-. Fe2 sulfide. Sulfide is in the chalcogens. It's an oxygen neighbor. And it has a 2- charge. So iron must have a 2+ charge. That's why we give it a Roman numeral 2. Lead 4 oxide. Right? Lead is one of those, it's not in the transition metals. It's over underneath the nonmetals, but it still has multiple charge. All right, how about this one? CrO2. Right? Type 1, type 2, type 3. It's a metal and a nonmetal. It's either a 1 or a 2. Then we look, where's chromium? Chromium is a transition metal, and it's not one of our 3 exceptions. So it has multiple charges. So we know it's going to be called chromium. And we have to designate the charge for the oxide. Well, 2- for each one of those. So what's the balance that we need? Well, 2 times 2- is 4-, so we need a 4+. There's only one of them, so that one has to be a 4+. Roman numeral 4. Okay. All righty then. Oh, another exercise. We're going to go back and dredge up some skills that you learned in chapter 4. What's the correct name of the compound that results from the most stable ion for sulfur and the metal ion that contains 24 electrons? All right, so we got a metal ion, or we could say, let's do this. Here's our metal. There we go. And it's bound to sulfur. Okay. And the sulfur is in the oxygen group, chalcogens. So it's a 2-. Now, here's the problem with that question. It doesn't tell you how many sulfurs. So we have to assume that there's only one. Results from the most stable ion of sulfur and the metal ion. So there's one of each. 2-. That means this one has to be a 2+, and it has 24 electrons. Okay. How did it get a 2+ if it's got 24 electrons? that means it has two more protons than electrons, right? It's not balanced. It has two protons, which gives it the 2 plus. So two more protons would be 26. And we go to our periodic table, look up 26 as the atomic number, and we find that it's iron. There's your compound. What's the correct name? Iron 2 sulfide. Okay. All right. There's another giveaway. If you're naming compounds, and I see you name a compound like this, not FIDE, you name it SULPHIDE. I know you looked it up in the internet. You didn't name it yourself. You looked it up, you put it down there expecting to get credit. You won't get credit for it. Because on this side of the Atlantic Ocean, we use an F, not a PH. All right. Type 3. Now we're finally getting to type 3 compounds. Two nonmetals. So both of the binaries have to come from, both the elements have to come from the right-hand side of the periodic table, on the other side of that jagged line. We're going to borrow convention from type 1 and type 2. Treat them as if they're metal nonmetal, but they're not. We know that. But we put one of the names first, one of the elements first, and then we take the second one and convert the N to IDE. Okay. Now, since they're not charged, there are no charges, no positives, no negatives. We have to say exactly how many of each atom is in the formula. That's just a fact, right? Since they're not charged, we can't balance charges. So we have to actually say, to be unambiguous, we have to say exactly how many there are, and we use the Greek prefixes for the numbers. All right, those should be coming up. Prefix mono means 1, but it's never used on the first element. Well, I'll give you an example in a second. There are your Greek prefixes. Memorize them. If you don't already know them, mono, di, tri, tetra, penta, hexa, hepta, octa. I left off 2 of them. Nona for 9 and deca for 10. Okay, so for an example, if we have this compound, we know it's type 3 because carbon and oxygen are both nonmetals. It can't be 1 or 2. It has to be 3. So that means the way it's written, carbon comes first. There's only 1 carbon, but it's first, so we don't say mono. It's just convention. But we do say dioxide for 2. Sulfur, hexafluoride. 6 is hexa. Hexafluoride. Now, when we have more than 1 in the cation position, we do say how many? Dinitrogen, then tetroxide. Notice we don't say tetraoxide. It just doesn't sound right. Chemists have sensitive ears too, so we say tetroxide, not tetraoxide. Okay. Let's name this compound SeO2. Give ourselves some room here. SeO2. Okay, first question. Metal, non-metal, or non-metal, non-metal? We know where selenium is located, right? So we look, right? It's a non-metal, so it's a type 3 compound. Okay, so we say selenium, dioxide. All right. Very simple. Follow the rules and you can't get lost. There's a there's a decision chart, flow chart, and it tells you exactly what I've told you to do. First thing you do is look for the metal. If you don't find a metal, if you do have a metal, then you've got to differentiate between type 1, type 2. If you don't have a metal, then you automatically go to type 3 and use the prefix for the numbers. Now, before we get to polyatomics, if you've got a compound of 2 nonmetals and you're not told which one comes first, okay? Say you have, let's see. Phosphorus and oxygen. Say you have phosphorus and oxygen together. Which one comes first? By convention, the one that's to the left and or below the other one comes first. It has a more metallic character to it. It's not a metal, but it has a metallic character. So phosphorus is to the left and below oxygen. That means it would come first. Then you have to be told how many, of course, because they're both nonmetals. So that just gives you the order. It doesn't tell you how many. An example. P2O5 is a very common compound. Find it in fertilizers, right? No fertilizers have 3 numbers on them. If you buy them in the grocery store or Walmart, you may find them as 10-10-10 or 5-5-5. Well, those are N. The first one is nitrogen percent, like 5%. The next one is phosphorus, but it's P2O5 phosphorus, 5%. And the last one is potassium, but that's K2O, 5%. Okay. So when you look at a fertilizer bag, you're not looking at NPK, you're actually looking at N, P2O5, and K2O. All right. So we've described binary compounds as 2 elements. But there is a class of ions that are covalently bound 2 or more elements that have a charge, a fixed charge. These are polyatomic ions. And your review document has a list of them. Let's see, I can show you that list here. This is what they look like. I've got a slide, but the slide is kind of small. There's a list. There's a list on one side and the other side, and they're duplicates. This is all the polyatomics that we're going to need to know. And this is the same list, only this side is organized alphabetically by their names. This side is organized alphabetically by their formulas. These polyatomic ions are, like I said, a covalently bound group. And the charge that they bear is distributed over the entire group. So if you have a polyatomic ion that's two elements, like this, with a -1 charge, that's hydroxide ion. That charge sits over here, but it's not localized on the oxygen or the hydrogen. It's distributed over the entire group. That means when you put it into a compound or you see it in a compound, you cannot break it up to make the formula balance. You must retain polyatomics as a single unit. Okay, I'll show you what that means in just a second. They do have special names. The slide says you have to memorize them, but you will always have that list available to do your homework on the tests. If you take a paper test in class, you'll have that polyatomic list in useful information in the back of the test, just like it is in the review document. If you take the exam in Brightspace, then before you open your exam in Lockdown Browser, in that same module is useful information document. You're allowed to print that document and keep it with you while you work your exam. The reason I put it there is because once you get into Lockdown Browser, you can't go anywhere but the exam. And I can't load that useful information into the exam. So I'll let you keep that document with you. Okay. So these polyatomic ions have special names, and there's a pattern to them. Much of the pattern is derived from medieval times, but we tried to standardize it anyway. Okay, hydroxide is one of them. All of the ones on that list that I give you are minus charges. They could be -1, a 2-, a 3-. There's only one in there that's a positive. The one positive polyatomic ion is this one. That's ammonium. And you don't modify the name of polyatomic ion. When it goes into your compound, it retains its name, complete and unchanged. So if we have ammonium combined with an anion, like chlorine, right? That would be ammonium chloride, right? Notice that's a type 1 compound because we don't have any Roman numerals in here. We don't need them. Ammonium is a fixed charge, so we treat it like a type 1 compound. All right. Those are examples. Stick to my chart. It's better organized. Yeah, there's the only positive one. The rest of them are negatives. But some do form logical groups. For instance, if you combine chlorine and oxygen together, you can get this list of 4. I always start with the chlorate. Let's see. Yeah. Chlorate, which is ClO3-. If we remove an oxygen, then we change the name to chlorite. It's still a -1 charge. If we remove another oxygen, we don't have any more suffixes, ites and ates, that's all we have to go on. So we use a prefix. We say hypochlorite, which means underneath, like hypodermic, under the skin. This is under chloride. We've lost one oxygen. We can also add an oxygen. So if we add an oxygen, we also need a prefix, perchlorate. Per means bigger than. So it's one above the chloride. And that list, if you memorize that format, you've got 4 polyatomic ions memorized now. And chlorine is a halogen. You can substitute other halogens in there. Say we have substitute bromine, bromate, perbromate, BrO4 minus, right? So now you have all the bromates, polyatomic ions memorized. You can substitute, fluorine doesn't work, but iodine does. You could say per iodate, and it would be IO4 minus. So there you have 12 polyatomic ions memorized already. There are others that give you a pattern. For instance, the nitrate, NO3 minus, take away one oxygen, you have nitrite. The sulfate is SO4 2 minus, take away one oxygen, you have SO3 2 minus is sulfite. Then you add a hydrogen to it, to the sulfate, and that reduces the charge from 2 minus to 1 minus. That's hydrogen sulfate. Bisulfate is not acceptable. You'll see it, right? You'll see it on packaging. Sometimes it's even used on chemical packaging when you receive your pure chemicals from the supplier. But hydrogen sulfate is the proper name. If you use bisulfate, I know you looked it up. And you didn't name it yourself. There are other possibilities, and we'll experience those as we proceed. There's the chart. See, it's too small. I wanted to get the whole thing on there to show you how it's organized. Okay. When we use polyatomic ions, we simply name the polyatomic. Similar names, right? The cation comes first, anion comes second. So this is ammonium acetate. The acetate ion is C2H3O2 with a 1 minus charge. And that's all you have to say. That's unambiguous and not redundant. Sodium hydroxide, right? Type 1 compound. Sodium is a fixed charge, so we don't need a Roman numeral. Sodium hydroxide. We just balance the 1 plus charge from sodium and the 1 minus charge from hydroxide. Notice for this one, magnesium nitrate. Yep. Nitrate is a -1 charge. Magnesium is an alkaline earth, so it has a 2 plus charge. So how do you get that charge to balance? Change that to 2 and that to 6, and that'll give you another charge? No, you can't do that. This is a covalently bound unit. It behaves as a single unit. We actually should do something like this, say X minus. How would you balance X minus and 2 plus? You would put a subscript like that. Well, when you have multiple elements, you have to put a parenthesis to give it 2. Okay? If you don't do that, it's wrong. Ammonium sulfate goes the other direction. So this time the cation has a +1 charge and the anion has a 2 minus charge. So you have to have parentheses. Now, parentheses are not bad. They're necessary. But if you see the compound NH4 taken twice, sulfate, SO4, then that tells you that NH4 is a polyatomic ion, the way it's written. NO3 taken twice is a polyatomic ion. That's a clue to tell you that you're dealing with a polyatomic ion, and you need to look up the name. This one's not so straightforward because phosphate is a 3- charge and iron happens to be a 3+ charge because there's only one of each. If you have a compound with 3 elements in it and one of them is an oxygen, suspect polyatomics. Okay, there's your flow chart, your decision tree. How about this one? KClO3. KClO3. Right? 3 elements, one of them is an oxygen. I suspect that ClO3 is a polyatomic ion. So you go look it up and you find out that it is chlorate. Right? How about potassium? Type 1 or type 2? Type 1. It's a +1 charge. This is a -1 charge, +1 charge. So we only need to say potassium chlorate. That's our name. Unambiguous, non-redundant. All right. Oop, there's another one. Okay. Examine the following table of formulas and names. Which of the compounds are named correctly? Okay. You got to decide. 2, 3, 4, 1, 2, 3, and 4. All right. How about the first one? P2O5. Type 1, type 2, type 3. Type 3. So we're going to say diphosphorus pentoxide. Is that correct? Yep, that's correct. Next one, ClO2. Type 1, type 2, type 3. Type 3. Right? Non-metal, non-metal. We have chlorine. Now this one sort of skews the rule I gave you earlier. Chlorine is below and to the right of oxygen, but we still put it first. So that rule I gave you about to below and to the left comes first is to help you out if you can't make a decision. But if you're actually given the compound, then you go with what you're given. So chlorine dioxide. That one's wrong. Okay, which ones are correct? Well, so far, Roman numeral 1 is correct. Roman numeral 2 is wrong. How about PBI4? PBI4. This is a halogen with a -1 charge, so this one has to be a 4+. And lead is capable of multiple charges. So it's lead 4. Let's see. Capital. Iodide. Okay. And that one's wrong. And the last one, CuSO4. There's a polyatomic ion with a 2- charge. So that means this copper has to be a 2+. Right? And copper is one of those that has more than one possible charge. So we do have to say copper 2 sulfate. Okay, copper 2. Oh, that one's wrong also. So the only one that's right is number 1. Okay. Now naming acids. This naming convention was probably one of the stickiest resolutions that the IUPAC naming committee had to deal with, because several acids had been identified and named in medieval times before they came to modern chemistry. So what we had to do is, definitely with naming acids, we had to figure out a convention that would satisfy the names that were already being used and allow for extension to other names. So when you name an acid, you have to decide, do I have an acid? All right, so I'm gonna have to erase the rest of this stuff, and then we'll get to acids. That just makes a mess. See if I can clean that up a little bit. There we go. Okay. Clean surface. All right, acids. First thing you have to do is identify whether or not you have an acid. Acids always start with hydrogen. Okay. It could be 1H, it could be 2, it could be 3. I've never seen one with 4. And then you have something else on the tail end of it. But it always starts with hydrogen. This is the hydrogen that breaks away from the molecule and causes acidity. In other words, if you taste an acid like vinegar, it's sour. It's sour because your taste buds detect the presence of that hydrogen ion. So our acids have to start with hydrogen. Now there are 2 types. We divide, for naming purposes, we divide the names into 2 different types. Let's see. Here we go. One is it does not contain an oxygen. So our example was that one. Now, how would we name that if we didn't name it as an acid? If we just named it with a type 1, type 2, type 3 convention? Well, it's a fixed charge, right? So we would say hydrogen chloride. Okay? But if it's dissolved in water, this is a gas at room temperature and pressure. Dissolve it in water, now you have the potential for some of those hydrogens to be removed from the molecule and deposited in the solution. So now the convention is, if there is no oxygen in the molecule anywhere, then we start the name with hydro. and we take the ending of this name and we say, instead of chloride, we say chloric, and end it with acid. So that's hydrochloric acid. We've got polyatomic ions also, right? If we had this one, and it was not dissolved in water, then we would call this hydrogen cyanide. But if we dissolve it in water, we take that gas and bubble it through water, it dissolves in the water. Now we have an aqueous solution, right? We started with hydro, right? Because there's no oxygen. And instead of IDE, we say cyanic acid. Okay? That's the convention for no oxygens. H2S, hydrogen sulfide. So we would say hydro instead of ide. We modify the name a little more extensively. Instead of hydrosulfic, we say sulfuric. Just sounds better. Hydrosulfuric acid, H2S. There's some other examples. Some more halogens, right? Hydrofluoric acid, hydrobromic, hydroiodic. Okay. Now, if they contain oxygen, we go to our second rule. We leave the hydro off. We don't say hydro. If there's oxygen, we do not say hydro. Instead, we look at the anion end of the molecule, like how about this one? Remember that polyatomic ion is chlorate? Then if we have hydrogen, we would name it hydrogen chlorate. But if we put it in aqueous solution, now we ignore the hydro part and we look at this, chlorate. 8, we change the 8 to ic. And we just say chloric acid. That's it. Or HNO3 would be hydrogen nitrate. This is nitrate. Polyatomic. And obviously, if there's oxygen in there, you're dealing with a polyatomic ion. So we say 8 becomes ic, we say nitric acid. That's if it's in an aqueous solution. Okay? Or sulfate, this is sulfuric acid. Remember, H2S was hydro sulfuric acid. Whereas H2SO4 is simply sulfuric acid. Okay. And the difference is the oxygen. C2H3O2 is the acetate ion. So we would say HC2H3O2 in aqueous solution, we take that, acetic acid. All right. 5% equals vinegar. Okay. That's if the ending is 8. 8 becomes ick. If the ending is ite, like H2SO3, right? This is sulfite. Then the ite becomes us. Sulfurous acid. Okay. Or NO2 is nitrite, nitrous acid. There's a sulfurous acid. ClO2 is chlorite. Rather than chlorate, it's chlorite. So that would be chlorous acid. What if you had, let's see, let me see if it's in here. No. What if you had ClO like that, HClO? Well, that's hypochlorite. So you keep the hypo and you simply say hypo, this is aqueous, hypochlorous acid. Okay. Or if you have HClO4, this would be perchloric acid. Okay. That one, if it's in concentrated form, is extremely hazardous. It's a very strong oxidizing agent, which means if you combine it with an organic compound of some kind, and you're not careful, if you don't treat it correctly, you could get an explosion or a rapid exothermic decomposition. So I used to use perchloric acid in the lab to digest plant material. Very effective. But I couldn't just put it on the plant material and heat it up and go to town. I had to do a pre-digestion. So instead, I used a safer acid for a pre-digestion. I used cold, concentrated nitric acid. Nitric here. I think it was 70%. And I put that on my plant material in tall beakers, set it on the hot plate in the hood, turned the hood on, pulled the sash down, and I left it cold overnight. And it did a partial digestion. Then I added some perchloric acid the next morning, turned on the heat, perfectly safe. And what it does, it destroys all the organic matter and leaves the mineral ash behind. That's what I wanted, the ash. Now, if you take concentrated perchloric acid and you put it in say, a tall beaker, they're called Berzelius beakers, and you take a nice big chunk of butter, throw it in there, put it on the hot plate, crank the hot plate to high, pull the sash down, and evacuate the building because it will blow. All right, so there's your naming convention rules. First, you have to say, is there oxygen? If there's no oxygen, then you start the name with hydro. And you change the ending to IC, ick. And remember, these are all in aqueous solution for our purposes. If there is an oxygen, then you check the ending. If the ending is ATE, it becomes ick, and you don't say hydro. You just add the ick on the end and acid. If it's ITE, then you add the ending as OUS, acid. And then if there are any prefixes, of course, you have to include those like hypo and per. Okay. Which one of these is named incorrectly? Let's see. I got till 11. We're probably going to finish today, so we can start review on Thursday. So which one of these is incorrect? Let's make some room. And put a thin coat of WD-40 on this board. I think that'll help it a little. Okay, how about this one? So this exercise includes everything that we've learned up to this point, right? So you're not boxed in. You have to use all the rules you've learned so far. So this one would be what? Type 1, type 2, type 3. Potassium is a fixed charge, so it's type 1. All we have to say is potassium nitrate. That's your polyatomic right there. That's correct? Yes, correct. How about B? TiO2. TiO2. Type 1 or type 2, right? It's not type 3 because titanium's a metal. So it's 1 or 2. Well, where's titanium located? It's a transition metal. So it has to have charge designation. So we say titanium. And we're going to have a charge, oxide. The oxide is a 2 minus, so that's -4 here. That means +4 there. This should be a Roman numeral 4. That one's wrong. Okay. C. SNOH 4. Hydroxide is a polyatomic, so we have parentheses. Each hydroxide is a 1 minus charge, so this has to be a +4 to balance it. So this would be 10, 4 hydroxide. Right? Type 2 compound. That one's correct. D. PBr5. PBr5. 1, 2, or 3? 3. Phosphorus and bromine are nonmetals. We've only got one phosphorus. Now in this case, we do use the pH. pH and pH. That's correct. And this is pentabromide. Is that correct? Phosphorus pentabromide? Yes. How about the last one? H2SO3. H2SO3. Now, we're going to name it as an acid, but technically it should have aqueous behind it. It should be aqueous. There's an oxygen, so we don't say hydro. We simply take this one, which is sulfite, and ite becomes us. So we say sulfurous acid. Okay, that was correct. B is the only bad one in there. Okay. Sodium hydroxide. And when you write that formula from the name, is a type 1 compound with a polyatomic. So we simply say sodium hydroxide. All right. Potassium carbonate. There's potassium. What's carbonate? You might have to look it up. It's a type 1 compound. This is only a fixed charge. Carbonate is CO3, 2 minus. So that means we need 2 potassiums. You don't have to put the charges in, though. That's just for balancing purposes. Second one, sulfuric acid. So sulfuric, notice there's no hydro. So we know there's an oxygen in there. Ic is derived from ATE. So sulfate is SO4, 2 minus. And it has to be an acid with 2 hydrogens to balance those 2 minuses. Okay. And of course, we should introduce aqueous. The giveaway here, di and penta. That's a type 3 compound. Dinitrogen, pentoxide. Okay. Is there another one? Yeah, there's cobalt 3 nitrate. Cobalt is that. It has a 3+ charge. And nitrate is a polyatomic ion, NO3 minus. Okay. So to balance that one, we need 3 of those. That's it. Okay. There's a little detective work coming up. A compound has a formula XCl3. Right. So this could be a metal or a non-metal. We don't know yet. X could represent, well, that's what the problem says. What could the name of this compound be? We need more information, don't we? Oh, we get to choose. Okay. So this is multiple choice. That means that either this is a non-metal, and we would say trichloride, right, with something here. Or if it's a metal, we might say the metal could be chloride, or it could be chloride with a charge for the metal, X here and X here, and then whatever X has there. So do we have a trichloride in there? Yeah, we have a phosphorus trichloride. That would work, right? Phosphorus trichloride, A could be it. That's possible. Carbon monochloride, no. Tin 4 chloride, no, because there are 3 here. Tin 4, let's see, SN4 would be, or tin 4 would be SnCl4. Can't be that one. Magnesium chloride. Magnesium would be here, and that would be 2. Okay, so the only one that works is A. Okay, we had process of elimination. We had to say which is possible, right? We know the chloride, but what else could we put with it? Carbon, tin, magnesium, right? None of those names work for our formula. That's how we decided that one. Okay, the last naming convention, I added this slide in. The original slide set didn't have it. There are certain compounds, primarily type 1s and type 2s, that when you are preparing them, they have some moisture in them. Okay. Say you precipitate out a salt in aqueous solution, and now you want to dry it down. So you filter it out through paper, and then you put it in the oven at 105 degrees Celsius. Why 105? Because the boiling point of water is 100. So 105 should drive off all the free water. Okay. What we discovered, chemists discovered early on, was that if you heat the compound up to a higher temperature, like 150 degrees, right? This evolves some water. This evolves more water. So the water here that released at this higher temperature was some way bound in the crystal structure of the compound, of the ionic compound. This is called waters of hydration. So once we determine the ratio, the molar ratio, that is moles of water per moles of compound, then we can write the compound in this fashion. Okay. You write the compound first without the waters. So zinc sulfate, for example. Okay. This is a type 1 compound because zinc is one of those transition metals that has a fixed charge. It has a 2+ charge. And this is the polyatomic with a 2-. So that's how you would write it, ZnSO4. Then you either have to determine experimentally, or if you're told how many waters are attached to that zinc sulfate or in the structure. And in this case, we have 7 waters. For every 1 unit, for every 1 formula unit, we have 7 units of water. And then you connect them with a dot. That dot's in the middle of the line. It's not on the line. It's not at the top of the line. It's in the middle. That means, and you name it, first you name it this, zinc sulfate. Then you use your Greek prefixes. 7 is hepta. Hepta hydrate. That would be the proper name for that compound. Let's see. Let's go backwards. What if you had, let's see, copper. Let's see. What if I did copper 2 sulfate, not hepta, pentahydrate. We would say CuSO4. This is a 2-, this is a 2+, so they're good just like that. And then pentahydrate. Okay. All right, that's how you name waters of hydration for compounds. And they're always either type 1 or type 2. So they're metal, non-metal.